Morning everyone. Yes, I'm still here, we're still planning on learning stuff. I've been using this method with my Year 12 A-level students for the past 3 or 4 days and they've been engaging with it really nicely. This video will be going on a forum, of course, and that's where a lot of the work I'm asking you to do in the next few weeks will appear. So, I'm not actually going to do a huge amount with this video because the PowerPoint's pretty good to take us through the next part of the electrochemical potentials booklet. Okay, so we're doing some of this today. I'm going to try and do it all in one take, which might mean a few slip-ups and things, so bear with me. In fact, I'll check that we're actually recording, which we are. So have this booklet ready and the work you've been doing on it. Those of us who were here last week have already done things about the different types of battery, so I'm not going to go over that again. We're going to talk about fuel cells, which is another application of this sort of chemistry. So, I've brought with me something we were doing last time. So, at the start of this topic, we looked at some zinc and copper dipped in solutions of zinc and copper ions. So, those two solutions in this example were called our electrolytes. That's where the ions can move around, okay, and could be split up if we put a current through it. But those are our electrolytes. That's going to be important in a minute. And these were our electrodes, the bits of zinc and copper. Or if we couldn't fit zinc and copper in, we'd have to use some platinum. If we didn't have any solid we'd have to use platinum. That enabled us to make this representation of the cell, okay, with our most oxidized form of our metal here, nearest the salt bridge, and then our least oxidized bits on the outside. Okay, that's where we got to last time. We're going to talk briefly today about a similar diagram for a fuel cell. If I can stand that up. Now the difference with a fuel cell is that the chemicals that we're interested in are being supplied from outside and being sort of pushed inwards. So you're going to want page 10 of the booklet because you've got a diagram of it there. I'll hold it up to you now. So if I can just check there. There we are, so that's the thing we're after. Now this is called the alkaline hydrogen-oxygen fuel cell because we're under alkaline conditions and obviously it's using hydrogen and oxygen. So we can use this to power a car if we wanted. So it looks different, but we've got 2 platinum electrodes here. Okay, so those are our platinum electrodes. The setup looks different, but actually it's the same thing. They're kind of sharing the electrolyte here. Okay, so 1 shared electrolyte and 2 electrodes. Now, between the electrolyte and the electrode itself is a sort of semi-porous membrane that would allow the hydroxide ions to move across. Okay? So, have that in front of you. The idea is that we can take the hydrogens from one side and do a reaction there with some hydroxide ions. The oxygen's coming from the other side and is donating some of those electrons. You're going to see those when you look at the booklet in full, so I'm not going to go over that in detail. What we will go through is how this can then be represented as a cell. So obviously overall we've got electrons moving from one side to the other, and as it starts to run out, or if this reaction looks like it's running out, we just pump more fuel in. So the fuel is supplied constantly, the H2 and the O2. Okay? In the case of the rechargeable batteries, we didn't have that option. We had to plug the battery back in and send the electrons back the other way. This time we just keep supplying the raw materials. So, now that we've got all of those, we can start to look at doing this, but for that diagram you've got in front of you. So, again, we'll be starting on the left-hand side. So if you look back at your notes last time, we decided which was going to be the left-hand and which the right-hand side and why. But for us, that's the hydrogen end. So no electrode, no solid hydrogen electrode, so we need some platinum in there. And the least oxidized form of the hydrogen, the stuff that's being blown in, is obviously the hydrogen gas. I'm going to run out of space here, aren't I? Never mind, if I run out of space, I'll just carry on as you're used to seeing me do. Hydrogen gas coming through there. Now, there is a phase separation with the solutions that it's then interacting with. So it's a solution of potassium hydroxide. So we've got potassium hydroxide dissolved in water. It's the OH minus ions that we're interested in. There, aqueous. And we're also forming some water, so we're interacting with the water there as well. Okay, that takes us through that half. That's what's going on at the left-hand side of your diagram. Oops, sorry. We can still treat the electrolyte and the membrane as a salt bridge, so we can have that double line there. And that takes us here to what's going on with the oxygen, so I'll jump down a moment. Well, the most oxidized form of the oxygen is actually oxygen in oxidation state 0. So that's the oxygen gas that we're feeding in. So even though that's not quite how you might think of it from looking at that diagram, because of that oxidation state, that's where it goes. Phase separation with the same stuff that we've got here, but this time we need to put the H2O first. Aqueous. And then finally, of course, there's no solid oxygen electrode, so that's the other platinum electrode. Okay? Yeah. Right. So that's how we construct that overall conventional representation for the cell. You're going to have a go at some of the other questions using the PowerPoint and the booklet itself now, so I'm going to stop the video there. There'll be more instructions in the forum. Okay? Thanks for watching.